Welcome to this week's videos on our course Competition, Policy and Strategy. This week we are going to talk about the solutions to assignment number 3 on the topic of efficiency. Now in the first exercise we are going to look at production efficiency, and for this we are going to consider a very specific firm, right? So we are asked to consider a firm that produces a good, some quantity Q, some price P, using capital and labor. Capital, for the capital we will denote the quantity of capital that the firm is using in order to produce the good with a capital K, and the price of this capital per unit is called R. For labor, we will call the quantity of labor that is used as an input within capital L and the price with a lower W. Now we furthermore know the production function of this firm, namely we know that Q equals a function of capital and labor, so K and L, and this function reads as follows: K to the power of 2/3 times L to the power of 1/3. We then know that both factors of production are variable, so that the firm can choose not only the labor as we commonly assume, but in this specific case the firm can also choose the amount of capital it wants to employ even in the short run. Right, then this is just a technicality. We will in the following assume that there is perfect competition in all relevant market. That means that the firm is price taker in both the output market, so where it is selling the good, as well as in the input market, so where it is demanding labor and capital. Alright, in this first task we are asked to name the type of function that has the structure which we just saw in the previous slide. So the structure of the above defined production function. We are asked to elaborate on what characterizes the returns to scale of function of this kind, of this very specific specification. Okay, but first, the production function in general is understood as the maximum output as a function of the amount of inputs. So, as mentioned earlier, in this specific case we consider a situation where the firm can choose capital and labor as input quantities, and the production function then provides the maximum quantity possible that the firm can produce using any given combination of K and L. In this specific case, this type of function where we see some parameter x to the power of alpha times some other parameter y to the power of 1 minus alpha is called a Cobb-Douglas production function. Right? So x to the power of alpha times y to the power of 1 minus alpha is of course exactly what we see here. We have k to the power of 2/3 multiplied with L to the power of 1/3. This structure. Alright, so we are looking at the Cobb-Douglas production function. In the next step we're asked to talk about the returns to scale. But first let's have a brief reminder on what actually is returns to scale and how we can understand it. Okay, so a quick recap on returns to scale. The question returns to scale wants to answer is what happens to the output when the input is multiplied by some factor. So in general there should be 3 possibilities. Well, either the first possibility would be that input and output change with the exact same factor. So we have constant returns to scale. Or in other words, if inputs increase by some factor gamma, then the outputs increase by the same factor gamma as well. Okay, now the second possible situation would be that we have decreasing returns to scale, meaning, of course, that we have an underproportional increase in outputs, underproportional to the increase in inputs. Or in other words, if the inputs increase by a factor of gamma, then the outputs increase by a factor that is smaller than gamma. And then, of course, finally, the third and final possible world we can live in is increasing returns to scale, which of course is the exact opposite of the previous case. So in this situation, we know that if inputs increase by a factor of gamma, then the output increase by even more than factor gamma. All right. So in what world do we live in, given the production function that we defined in the exercise we are discussing right now? In order to find out whether we have increasing, decreasing, or constant returns to scale, we have to multiply our inputs by some factor. Let's name this factor gamma, just as we did before. All right, so we consider a situation where we want to find out what is the output for any amount of inputs, k and l, which are multiplied by a factor of gamma. All right, so we want to know what is the output of this function. Given we have we have a quantity of inputs that is gamma times capital and gamma times labor. And if we do this, well then, of course, simply by plugging in these values into the production function we defined and discussed earlier, we get this first expression, right? So we have gamma times k to the power of 2/3 multiplied with gamma times l to the power of 1/3. What's happening next, or in the following two steps, is that we simply rearrange this expression, right? Because this is two factors, we can put the power onto each of these and thereby get rid of this expression in braces. And the third step is just simply rearranging as well. And what you will notice once you go through all of these steps is that you can rearrange this initial expression, where gamma was simply a factor in front of the inputs, respectively. We can rearrange this expression to this down here, where we have the initial production function, right, multiplied with this factor gamma in the beginning. So, what we now know is that if we multiply each input by some factor gamma, then by the way we specified this production function, the output equals the same output that the function gives without putting in this factor gamma, multiplied with factor gamma, right? So, in this specific case, because the exponent of this factor gamma is 1, so we have gamma as an input multiplicator, and then we have gamma to the power of 1, so simply gamma as an output multiplicator, we know that we have a constant return to scale. In other words, another way to phrase this is the degree of homogeneity, because this really is what we are talking about right now in a mathematical sense. As economists, we of course use this tool set in order to find the returns to scale of a production function, but the method in itself simply is checking the degree of homogeneity of any function. So in this specific case, the degree of homogeneity is 1, which is interpreted as follows. All right, so we found out that the degree of homogeneity is 1. So in this specific case, we have constant returns to scale. And because it's constant, another way to phrase this is we can call this a linear homogeneous production function, right? So I talked, I tried to lay out or explain earlier that what we are doing here in a more mathematical sense is we are simply checking for the degree of homogeneity of the function, and in case we have a degree of 1, we also call this result a linear homogeneous production function. Okay. And this, of course, cycling all the way back to the start of this exercise, just for a second, and as a quick add-on, giving this type of production function where we have some factor to the power of alpha multiplied with some other factor to the power of 1 minus alpha, right? This kind of production function, or in other words, this kind of Cobb-Douglas production function, will always yield a degree of homogeneity equal to 1, simply by construction of the exponents. All right, just maybe fiddle a bit around with it, and you will find, or you will come to the realization that this must be true, for any alpha. Okay, and with that we are done with task number A. In task number B, we are now asked to state the cost minimization problem of the firm and to derive the first order conditions of the cost minimization, or of the cost minimum. And we are already helped in the task itself because we are already, the tool we need to use in order to do this is already named, namely the Lagrange method. Okay, so the minimization problem, the cost minimization problem. Well, in previous assignments, we were maximizing profits all the time. So we should already have a pretty good understanding of what it means in a mathematical sense to maximize a function. And of course, minimizing the function is the exact same, just with a negative sign, all right? So this first step really should ring some bell. The minimization problem in this specific case is, well, we have a cost function which is defined as the price of labor times the amount of labor we use as an input, plus the price of capital multiplied with the amount of capital, right? Because for each unit of labor we choose as an input, we have to pay the price of each of these units of labor, namely W, and the same argument holds for capital. Okay, so we have this is the cost function capital C of K and L, which reads W times L plus R times K. Now this cost minimization, trivially, if we forgot about what else is written on the slide, trivially becomes, or it takes the corner, or the solution would trivially be the corner solution where we use 0 capital and 0 labor, because in that case costs are simply 0. Okay, this is of course not the solution we are looking for, but instead we have to consider that the firm wants to produce a certain quantity, and given this certain quantity it wants to produce, it now chooses the input factors and substitutes these two input factors against each other until the costs that come with producing this certain amount are minimized. Okay, and this is what is happening on the second part of this equation. All right, so this Q really should be up there and not down here. Yeah, right. So we want to minimize this cost function which we're talking about, such that we have a production output which is at least at some value Q, and at the same time we know that by logic of this exercise both K and L need to be larger or equal, or weakly larger than 0. in other words, we cannot choose a cost minimizing quantity of labor of minus whatever. We cannot employ a negative amount of capital or labor. So we have two conditions in this exercise. All right, and from these two conditions, we can now state, or using these two conditions, we can now state the Lagrangian, which is simply the objective function, right? Where we have the cost function in the first part, and then because of the way we choose to rearrange it, we have this expression minus the Lagrange multiplier lambda, and in the brackets, in the braces, we have the condition we stated earlier. All right, so this is the Lagrangian, which we will call z, a function z, which is a function of capital, labor, and then the Lagrangian multiplier. Okay, giving this Lagrangian function, this z function, we can now calculate the first order conditions of this minimum that we are looking for. All right, so we have, of course, because we have three arguments in the function, k, l, and lambda, we have now three first order conditions, which respectively result from the partial derivative of this z function with respect of each of the parameters. So the first one is the partial derivative of z with respect to k. The second one is the partial derivative with respect to L, and then third and finally the partial derivative of the objective or Lagrangian function with respect to lambda. Of course, because this is the first order condition for the minimum, we know that each of these expressions needs to be equal to 0 in order for any given point to be an extremum or a candidate for the minimum. All right. Now in part C, we're asked to calculate, based on these first order conditions, we are now asked to calculate the conditional factor demand functions, which we define to be k, or factor demand for capital, as a function of the price of labor, the price of capital, and the quantity we want to produce. This is why we call it the conditional factor demand function. So factor demand for factor capital condition on the quantity Q we want to produce. The same, of course, for the second factor we want to consider, so labor L, as well as the cost function, which the conditional cost function, conditional on the quantity we want to produce, then results as a cost function capital C as a function of cost of labor, cost of capital, and the amount of output we want to produce. All right. Now, how can we do this? Well, let's have a look at the previous slide once more. We know from we have these three first order conditions, and in these first order conditions, we already have all we need in order to find the conditional factor demand functions as well as the cost function. Right? We already have some expression where we can put k on one hand side and all other variables on the other hand side, and then you will notice, well, in each of these two expressions we have a k as well as L, but then of course we can substitute these for one another. Okay, but one step at a time, let's have a look at how we can actually do this step by step. Okay, so let's first calculate factor demand functions k as a function of W, R, and Q, as well as L of W, R, and Q. One way of doing so is, as I tried to indicate earlier, by using the first and the second first order conditions. So these, of course, were the derivatives with respect to capital and labor, respectively. Okay. We can use these two, simply divide the first by the second, or the other way around, just as you prefer. I personally chose to divide the first by the second, and this yields this expression on this slide. Okay? Yeah. We can immediately see that we now have some expression where we have, or within this expression, we have L, K, W and R all within, and lambda of course, all within one single expression, all right? So this is the first step of yielding these expressions. We can then rearrange this expression and get these two intermediate results. Notice how each of these factor demand functions still depends on the second factor, right? And not on the actual quantity. So we're not quite there yet. But we can already calculate a factor demand which depends on the prices of the factors as well as on the second factor. Using these, we can then substitute for the respective other input factor, right? So we have an expression where we have, in the third first order condition, we have an expression where we have Q as well as both input factors. Okay, so we can rearrange this so that we have some expression that is K equals something that includes L and Q, as well as L equals something that includes K and Q. Okay, we can use this third first order condition in order to substitute away whatever input factor we don't want to have in our expression. Because we can, using this third first order condition, we can express K as something that only includes L and Q, okay, using the third first order condition. And that's exactly what we are doing on this next slide. So we are using the third first order condition in order to substitute away the respective other input factor in this expression on the previous slide. And doing this, we can then find that we have these conditional factor demand functions. All right. Now to the cost function capital C, and again we want the cost function, the conditional cost function, to be a function of the prices of the input factors as well as of the output quantity. So our initial cost function, which we already knew from earlier, right, the cost function that we started the cost minimization problem with, of course was a function of the prices of the input factors as well as the input factors themselves. Okay. Luckily, we have in the previous step derived expressions for these input factors, K and L, that only include the prices of these input factors as well as the quantity. Okay. So if we wanted to find an expression for the cost function that does not depend on K and L anymore, well, we can simply substitute them away. So plug in this expression for K in the cost function, right, and plug in this expression in the fourth line on the slide for L in the cost function, and we should get an expression that only includes factor prices as well as Q. And that is exactly what we're doing on this slide. Alright, so start with the initial cost function, which we already know. Total cost of the firm is the price of labor times labor plus the price of capital times capital. And now we substitute, just as I said a minute ago, we substitute for L as well as for K the conditional factor demand functions which we arrived on the previous slides, which we derived on the previous slide. Now this final step is some rearrangements and nothing else. So we have in the end, we have a cost function which only depends on the factor prices as well as on Q, which is exactly what was asked in the exercise.